Welcome, welcome. Very important lecture today because we're going to talk about exam one, right? We will start with the life hack of the day. And Ian today has graciously volunteered.
Okay, so if you're ever in an argument with somebody or work in customer service, try to have a mirror behind you. People don't want to see themselves be mean. So everyone who answers to you in an argument or like when talking to you, if they see themselves.
Very nice, very nice. That's a very useful tip. I'm going to put a mirror behind my head now. That's really awesome. Thanks, Ian. Great tip. Who wants to volunteer for next Tuesday? Come on, could be anything fun that you found useful. Volunteers, life hack. All right, Ainsley is for next Tuesday, okay? Thank you. Okay, so today's session is going to be mostly dedicated to discussion on exam one. We have over 150 questions that I was going through. Brooke and Nicholas were helping me as well, but I went through most of them today, and I'll show you. We'll go through some of them together in class. And all of the material you're going to see here today is going to be put on Canvas. Okay, and I will put a description for exam one to remind you and explain everything to you. And today's session is open to questions as well, so feel free to interrupt me during the discussion, clarify a point. It's really your time. All right, so I'll start first by kind of giving the obvious expectation for exam one. It will be closed books, closed notes, closed phones, closed technology, essentially. You're allowed a letter-sized, double-sided note sheet and your calculator. So take notes as you're studying, whatever elements you feel kind of fuzzy about, write them down on that note sheet. Please use a normal font size. Someone had a magnifier with them once to read the note size sheet. Lev.
We don't have to print though, we can
You can print it, you can write it, I don't care. It's as long as it's letter-sized and double-sided. For your calculator, please do not use it in advanced mode, at least for this exam. So essentially, you cannot do a vector norm using your calculator or an integral or a derivative, okay? If there's a complex derivative, I will give it to you. If there's a simple derivative, you're expected to know it. And you can use your calculator only to crunch numbers, multiply, divide, add, subtract, okay? You will be given any complex formulas that are needed, such as I'll give you the Thomas algorithm, Newton's method, finite difference approximation, whatever is needed that is complex. So don't fill your sheet with these formulas. I will give them to you. Now, clearly, if you're still kind of concerned about a formula, write it down. It's your note sheet. It doesn't bother me. Okay, so I'll give you like Newton's method, finite difference, the Taylor series, etc. The exam will be focused on the three chapters that we covered so far: error analysis, linear solvers, and nonlinear solvers. Okay, so included. We are not covering interpolation. That will be going to be on exam two. Okay, the exam will not include programming questions. So I'm not going to ask you how to use fsolve or what are the arguments to fsolve or how do you plot x versus y. I'm not going to ask you syntax questions. Okay, so in general, no programming questions. The only programming-like questions are going to be conceptual in nature. I'll give you a couple of examples here. So for example, is a while loop preferred over a for loop when calculating a Taylor series up to a certain tolerance? We discussed that in class, so you're expected to know that and explain why. Or for example, what inputs would you provide for a certain routine, like the Thomas algorithm or the Newton-Raphson algorithm? Also, those things were discussed in class, okay? So that's the only that's as close as we're going to get to programming. But do not waste your time on memorizing syntax or studying Python or any of that. Okay, I want you to focus more on the theoretical aspect and the kind of application side and understanding of numerical methods and how we use them. Okay. Then otherwise, everything covered in the slides and during class discussion and class work, you should expect to be asked about. Okay, so as you might have guessed from the quizzes as well, that paying attention in class, listening into the discussions we have when we're solving problems. That is very important, okay? So if you're iffy about anything, go back to the recorded lecture and listen into the lecture, at least participate, listen into the class discussion and see what comments were made, okay? And because you will be asked about those, all right? So in addition to the items listed below, it is important to have paid attention to class discussions and work done during lectures. And like I said, those are recorded, so feel free to go listen in, okay? This is a general study guide, which essentially just tells you roughly what to expect, or in general, what to expect to be asked about for the topics that we covered so far. So I would cover all of the learning objectives in each chapter. I know sometimes we went beyond the learning objectives. Sometimes we did not cover a particular learning objective, which I hope I had highlighted in red. If not, just if you're confused about it, just ask me, okay, as you're studying. In many of the slides, at least for linear solvers and nonlinear solvers, there's this section at the end that says additional material. You are not responsible for that, okay? You are not responsible for that. I'll give you an example. In the slides for nonlinear solvers, I mention closed domain methods or bracketing methods like the bisection and the secant method. That's all you need to know. I am not going to ask you what the bisection method is or what the secant method is. But I expect you to know that, a closed domain method is one where we bracket the root. A couple of them are bisection and secant method, okay? You want to study about the secant method and bisection, there's material at the end of the chapter, of the slides. That's up to you. But you're not going to be asked about those, okay? All right, so here I tried to summarize roughly as I put the exam together what to expect. Define absolute and relative errors, define true and approximate errors, identify the 3 types of errors encountered in numerical methods and analysis, so a round-off, truncation, and iteration error. Then for a mathematical expression, given the true value and an approximation to the mathematical expression, take what is the truncation error, which is the difference. For round-off errors, given the round-off error, calculate the accumulation of it. So I know that confused some of you based on the feedback that I received on error analysis. Just like the homework assignment for the Scud missile, I gave you, I had to calculate the round-off error. I gave you the error committed in one cycle, and then you had to calculate that as the clock ran through. So you'll be given that information. And then compute the Taylor series for a function up to a certain number of terms, like we did in class. We're going to come back to error questions once we hit the feedback documents. For linear solvers, identify what linear systems of equations mean and how they show up. Be able to write a system of linear equations in matrix form. That's really not part of numerical methods. Some of you were asking me about that in the feedback. That's part of linear algebra. And if you're still struggling with it, please come and see us. Talk to me, talk to the TAs, because you need to know how to do that, okay? Now, clearly, if I'm asking you to do the Thomas algorithm, I'm not going to give you 100 equations. I'll give you 3 equations, right, and 3 unknowns. So it's not really that hard to convert 3 equations to a matrix form, okay? Define and identify the different types of matrices. There were 6 that we showed on the slides. Okay, difference between direct and iterative solvers. We did not cover iterative solvers. And I'm not going to ask you about iterative solvers. There was one slide that said, direct solvers are good for all systems. They are robust, but they're expensive. Iterative solvers are good for sparse systems, and they only approximate the solution. That's all you need to know. Miles. We're going to hit that in the discussion, in the feedback. Thomas algorithm is not an iterative solver. It is a direct solver. Yeah, it is a direct solver. Connor?
Is it Newton's method an iterative solver?
An iterative method, yep, but it's not for linear systems, right? Yeah, but it is. Technically, it can be used for linear systems, but it is a type of iteration. So so essentially the difference between I know the Thomas looked like we are doing iterations, but we were not. We were just taking a sequence of steps. Each step led us to the exact solution. An iteration process starts with a guess and keeps improving it to get to the solution. With Thomas algorithm, we were not improving our solution because we didn't start with a solution. The first step in the Thomas algorithm was to convert the matrix to an upper triangular. There was no iteration there, no approximation going on. We did it exactly, okay? And then the last step was backward substitution. So no, Thomas algorithm is not an iterative solver, okay? Identify if a matrix is sparse or dense. In other words, calculate the sparsity of the matrix. Tridiagonal matrices, so you need to say like, yeah, this is a tridiagonal matrix. And the Thomas algorithm, and I will give you the Thomas recipe, the formulas that we wrote, that we had on the slides. Rearrange a system of equations into a form suitable for the Thomas algorithm. Lev.
You have to do that in like the recipe, like the equations that we used in class, or can you do it in like a more linear algebra way?
No, you have to follow the steps from the Thomas recipe, okay? Rearrange a system of equations into a form suitable for the Thomas algorithm. So if I give you 3 equations with 3 unknowns, right, and I put them in a certain order, you know, you don't have to build the matrix based on that order. You can simply move them around so that they're suitable for Thomas. What is suitable for Thomas algorithm or the TDMA is a tridiagonal matrix, okay? And then given a vector or array, calculate all 3 norms, L1, L2, and the L infinity norm, right? And finally, for nonlinear solvers, define what a nonlinear equation is, define what is meant by solving a nonlinear equation, define and write down the residual form of an equation, define what's meant by the root of an equation. All of those questions are asked in the feedback, so we're going to get to answering those for you, okay? Define closed and open domain methods for solving nonlinear equations here. We didn't cover closed domain methods this year. All we said was on one slide that closed domain methods, they say, okay, there's a root somewhere here. I'm going to bracket that root and somehow refine that bracket and home in on it. That's it. That's all you need to know about closed domain methods. Open domain methods, which is new, which we studied, the Newton-Raphson method is the basis of all of them. You start with one guess somewhere, one point. You don't have to bracket the root, just somewhere. Start somewhere and try to get your way towards the root, okay? Calculate the roots of an equation using Newton's method. In the exam, you might be asked to do a couple of iterations. So starting with x0, calculate x1, and then calculate x2, okay? Now be careful. In Newton, you already know how to calculate an error. One second. You already know how to calculate an error. So I might ask you, as you're doing the iteration, calculate the relative approximate error committed in your iteration, okay? So you should be able to do that. Emily.
I was just going to say, if we're given a Newton's method question, will we have an initial guess?
Yes, I will give you the initial guess or I will guide you through it. Yeah, that's a heavy burden to bear. Like in the homework, I gave you the initial guesses. Yeah, yep. Formulate the residual equations for a system of nonlinear equations. That's where the buck stops for systems of equations. For systems of nonlinear equations. For systems of nonlinear equations, we did not learn how to do Newton's method for systems of nonlinear equations. We used fsolve, right? Because it was just a little bit too complex right now to dig into that. So you will not be asked to apply Newton's method for a system of equations. You don't know how to do that, okay? If you're interested, they're in the backup slides. You're welcome to study those, but you're not responsible for that. When it comes to systems of nonlinear equations, all I will ask you is write them in residual form, okay? All right, so let's switch to the feedback questions. There's a lot. I know it feels like I'm rushing, but there's 3 documents. You see the tabs up there. Questions on errors, on linear solvers, and nonlinear solvers. And look at the questions, guys. So, and this has been reduced. We removed all the programming questions because you're not going to get programming questions. We deal with programming for homework assignments in the office and in the help sessions. Okay, these questions are to help with the theoretical foundation. So I have 3 of those documents filled with questions, and look at this one, 50 questions. So I'm going to try to be a little selective on these questions, and I'll answer them, put them in a PDF, and upload them to to Canvas and link to them. Those are the best study guide because they give me an idea of what was well received in the class and what was not, right? So it helps me design questions for the exam. Ethan.
Sorry, all we need to know is that we bracket an area.
That's all you need to know. Nope. You did not learn about that, and I do not expect you to know how to do that. So the exam is going to be 99% is going to be a Canvas exam. Okay, so you're going to be sitting here. You're going to have a lot of multiple choice or multiple answer questions. You're going to have numerical. So I'm glad you asked that. You're going to have numerical questions like calculate, do one iteration of Newton's method, put the answer up to one significant figure. You put the answer and you move on. Okay. So very low stake, a lot of low stakes questions. Okay. But there will be a few essay questions, like what inputs would you put for the Thomas algorithm, Brandon?
How many attempts do we get?
So far, you're going to get one attempt, but I might consider 2 attempts this year, okay? And it's going to be a short exam, so probably perhaps 30 minutes, so not the full hour and a half, but don't take that as a rule right now because I haven't finished putting the exam together, okay? No, for the entire exam, you'll just do the exam and then we'll just continue, okay? Okay, all right. Okay, so these are some of the questions. We took the liberty of editing some of the questions for more clarity. We'll continue editing. Many of the questions were similar, so we just kept one version of that question. And like I said, some of the questions were programming related, so we didn't answer them. Brooke and Nicholas helped me with some of these questions, and I worked on some of them. We'll go through them together. So identifying which type of error is dominant in a particular calculation. You always have round-off error. You always have round-off error. That's always given to you. If you are working with a procedure that is an approximation to an exact formula, such as computing a first derivative or computing a second derivative or taking 2 terms of the Taylor series, then in addition to round-off error, you have truncation error, okay? Iteration error is the vaguest of all, okay? And probably I'm not going to ask you about that because it's always vague. Even sometimes I ponder about it. But loosely defining the iteration error is the error between, so take Newton's method. Let's say your exact value of the root is 2.1. And you start your initial guess at 1.5. And then your next guess is 1.6. The difference between 1.6 and 2.1, that's iteration error. Then it's the difference between the current iteration value and the true value, okay? So it is a type of true error, right? But it's technically committed by iteration. As you iterate, iteration error is going to shrink, okay? But you still have the other types of errors going on, okay? I'm still a little confused why. Yes, Miles.
Iteration error for the most part is irrelevant.
It is relevant, but it's not very formally defined even in the discipline, because eventually iteration error goes to 0 once you hit the right solution. But round off and truncation will always be there. Okay. Once your iteration method cannot do any more, it cannot improve on the answer anymore, then there's no more iteration error. I'm still a little confused why we should not worry about round off errors, because modern computers have such high bits of memory, then in the vast majority of cases, you are not going to have to worry about messing up your numbers unless you commit a grave programming or human error, okay, where you manually convert a float to an integer and mess something up. But that's, well, all of the errors that happened in those systems were human errors. But if they had more bits, right, to deal with, then even a human error converting from a 128-bit to a 64-bit, it's not gonna cause any issues, okay? Because you have so many significant figures, so I wouldn't worry about it in real life. Okay, one thing on the current approximation. For example, homework on difficulty identifying current approximate value. Okay, so the current approximation is the value you're working with right now. and the previous approximation is the previous value. So say Newton's method, for example. X0 is your starting value. X1, you computed, that's your current approximation. X0 is your previous approximation, okay? And then you take that difference to define an approximate error. Now, one thing that was confusing, I think, to many is the confusion between sources of error and how we measure an error. So try to distinguish true error and approximate error as methods to report an error, okay? You could report a truncation error as a true error or as an approximate error. So approximate and true, relative and absolute, they're ways of reporting an error value. Now, where that error is coming from is a different story, okay? So if you remember the slides, the first chapter was measuring errors. So how are we measuring it? How are we reporting it? And then sources of error. So don't confuse the two. So a numerical method doesn't commit true error per se. A numerical method commits round-off and or truncation error, right? How you report the error is what tells whether you're reporting a true or an approximate error. Ethan?
So then, with direct solvers, do they not report truncation error then? They only have a round-off error?
So where, okay. So in linear you're talking about linear solvers, right? Direct solvers specifically, okay? Did we truncate anything? I just gave you a system of equations, right? 2x plus y equals 3 and 7x plus 8y equal 4. That's all you know. We didn't truncate anything. We just took that system and solved it. So as far as you know, this linear solver itself doesn't truncate a thing, okay? So there is no truncation error in linear solvers. There's only round-off errors, okay? Now you could report that round-off error, the error you're committing, as a true error, as a relative error, as an approximate error. That's an error reporting question, okay? Not a type of error question. What is the purpose of truncation error, and is it an error that can be calculated? So truncation error is something that exists. It's not like the purpose. It just exists when you take a full mathematical expression and cut it somewhere, evaluate a part of it. The difference, whatever is left, is your truncation error. Okay, it's a thing that exists. Okay, I don't think it's right to ask what is the purpose of truncation error. Perhaps the question would be, how could we make the truncation error useful? It tells us how well we can compute a quantity and what error we could be committing in computing that quantity. Because the first term in the truncation error, if you remember in the first derivative approximation, we had like an order h, right? It tells you that as you shrink h, that truncation error is going to shrink, for example. Okay? Okay. Okay, we talked about iteration, and I'm kind of skipping every other question. We will have answers to all of those before we submit. Okay, I had trouble completely understanding the total numerical error, like why round-off errors start to become big over time. That's a great question. So anytime you are measuring an error in any way, whether you're approximating it or you're verifying your method with an exact mathematical solution, anytime you're reporting an error, that you're always reporting the total error committed in the method. Okay, the round-off and or truncation, okay? That's it. It's just a definition. That's the total. It's total error or error, okay? That's a total thing, okay? Now, round-off might grow, might stay the same, okay? Or sometimes might shrink, depending on what kinds of mathematical operations you have. We didn't talk about this, and I'm not expecting you to know this. I don't even know it. I cannot even predict it, because whatever is going on in these algorithms, it happens so fast you can't tell if you're going to be adding or adding round-off or subtracting round-off. Sometimes you can subtract round-off and you get what's called a cancellation of round-off errors, and you shrink the round-off error. So round-off error is just there, okay? Now, we can dig into the depth of what's happening in these operations, but that's computer engineering, okay? Application of truncation error. Honestly, I had pretty good, okay? Mainly the wording on the assignment. Okay, this is, assignment was not clear. Well, okay, I want feedback on errors. I understood how the error was generated. Felt like unable to generalize examples to the other calculation. I think the confusion here was still between measuring and reporting errors and where those errors are coming from. Okay, distinguish the two. In a procedure, you have, let's say, I'm asking you to calculate, because by hand you're not really committing. I'm not worried about round-off error. You take an exact expression and you take a part of a Taylor series, and then I tell you, hey, report the truncation error. You could choose to report it as a true value or as an approximate value or a relative, right? So those are two different things, okay? Distinguish the two. Okay, so round-off errors, again. Why errors are important? Because we are approximating everything in numerical methods. And it's good to get a sense of what errors you might be committing in a system. And remember, when we started, we said we take a mathematical algorithm, we take a numerical algorithm, and how can we judge that it's good, that it's doing a good, it's doing what it's supposed to do? You develop a sensor to measure particulate matter in a room. How can you tell that it's measuring particulate matter correctly? You put it in a chamber where you inject a known concentration of particulate matter, and then you measure it and see what you're measuring, right? Right. So you know the true value, you know the difference. So that, and then you get a sense of the error, and then you take it to the real world, and then say, okay, when we measured this in a controlled environment, we committed this much error. That's the same thing here. Okay. And numerically, in most cases, we can actually get an approximation of what the error is. That was the concept of the approximate error, okay? Is truncation error different than round-off error? Yeah, so truncation and round-off are different. Round-off is only when you add, multiply, divide, or subtract numbers. That's it. Truncation is when you take a full mathematical expression and cut a piece out of it, okay? Okay, so this point, another point that I saw a theme reoccur is the meaning of the Taylor series. I don't know, perhaps I'm biased because I grew up in another country and we studied like Taylor series in high school, and I always think of people when they come to the university that they know the Taylor series. So the purpose, the Taylor series is a tool, okay? I know that many of you were confused, like if we have the exact formula and we can calculate the exact function or the derivative or that, why are we using the Taylor series? We're not using it for those cases. We use those cases just to illustrate how the Taylor series works and functions. But then after that, we started using the Taylor series to do things where we had no clue how to do. The Newton method, entirely based on the Taylor series. We had no clue how to proceed otherwise. And in multiple dimensions, we do the multidimensional Taylor series, and that's even more mind-blowing, and that it actually works at all. To define approximations of derivatives. And I remember Connor once asked, like, well, if we know the function, I think you asked that question, and then why are we computing the derivative? And then I said, well, we're going to, once we hit ODEs, we don't know the function. We're going to use the Taylor series to deduce what that function is, okay? So that's the power of the Taylor series. It's just a tool. How you use it, we use it in different ways, right? But the second point I want to make, in many cases, we illustrate the problem with an exact value, okay? That's to tell us that our method works, because it builds confidence. Again, go back to the sensor. You built a sensor. How can you tell it's measuring a reasonable particulate matter or whatever, radon, right? I have a radon sensor in my home, and I think I'm going to use the data for when we're doing integration. And like, how could I tell that radon sensor is measuring the right thing, right? I wish I had a chamber, put in a concentration of radon, right, and then tell it to measure it and see what it's measuring, right? That's how you do it. So yeah, Miles.
Is radon a radioactive gas?
It is a radioactive gas. It's found in all Utah homes. Okay. If you are renting a basement, definitely get a radon sensor. If you have a basement in your house and you spend time in it, get a radon sensor, measure the radon, and then perhaps install a radon fan. Okay. It's a big deal. In all houses, because the soil is kind of, I don't know, there's radon everywhere in the world, but and I live in Granite County. Well, not county. It's like in Sandy. It's like it's called Granite, the area, and there's a lot of radon in my house. It fluctuates a lot. I'll show you well, I need the Bluetooth. I don't have the data here, but anyway, I'll share the data with you. But okay. Well, it's a long-term exposure thing. Okay. Yeah. Okay, so this is the same question. If we have a real function, can model as a Taylor series, why would you use the Taylor series? We would not. We used it just to explain how the Taylor series works, guys, okay? This procedure actually has scientific literature in it. It's called verification. You verify that your method works on something you know, and then you take it out to the real world, okay? All right. What the Patriot system had to do with errors, I really don't know. It's like it's something that happened in life. The Patriot system had nothing to do with errors. Just those who programmed it, right, committed a mistake, and was a great example to motivate the study of round-off errors, okay? All right, so we'll continue answering those questions. We'll put them on Canvas, okay? So it's already like almost 2:30, okay. Now, let's go into linear solvers. Oops. Let me just fit this in. Okay. So how the TDMA works mathematically. So last year, I didn't explain that. This year, I hoped I had explained it. Apparently, I didn't. The idea is to combine the equations together to convert the tridiagonal matrix into an upper diagonal. Okay? So you take equation 2, multiply it by something, and subtract the 2. You knock out the term on the diagonal, and then you move on. You convert the whole thing into upper diagonal, and then back substitute. Okay? There's no magic going on there. How to mathematically calculate the inverse, this is not covered in this class, and that's a linear algebra question. Okay?
Will we ever need to know that?
In real life, if you know it, that's a good advantage, right? But, calculating it is very, from a numerical perspective, we rarely calculate the matrix inverse for large systems. Would TDMA be considered a superior method of solving linear systems, or does it have pros and cons compared to other methods, such as using NumPy solve or inverse matrix? Okay? So, here's my answer. As demonstrated in class with the heat transfer problem, TDMA is superior, both faster and cheaper in terms of memory. Okay, both faster and cheaper in terms of memory storage. Okay, when dealing with the tridiagonal systems. Okay, so TDMA only works for tridiagonal systems. It's a very special case of a direct solver. That's it. If you have a tridiagonal system, use TDMA. If you have a tridiagonal system and that's large enough and that you're using it, you have to solve it over and over again. Okay? So that happens in the case of partial differential equations. If you have to solve it over and over again, in class we solved it one time, right? And then we changed H. But when you go to time-dependent differential equations like PDEs, you have time and space. And at each instant in time, you have to solve the same heat transfer problem with different